Okay, how do I prove that any function is onto? Where do I pick an element to prove onto?
In the code domain.
In the code domain. So choose GH in Gmod H, right? That's what an arbitrary element in there looks like. To prove it's onto, what do I have to find? I have to find, this was an arbitrary element, I need to find somebody in G that gets sent here. Well, what is it, obviously? G. So I found a preimage. And I need at least one, but I found one. That's all I need, right? So therefore it's onto. While we're on the subject of preimages, think about this. What would be a preimage of GH? Would it just be G? Would G be the only thing that gets sent there? What would get sent there? Everything that's in there, right? If well, I should say it this way. Two cosets can be the same thing, right? That's possible. We did this lots of times when we were building cosets. You can get lots of different generators that make the same coset, right? And K is also. Because K gets sent the same place because K makes the same coset. Right? So I get lots of, this is a big set. In fact, the size of this set is the size of GH. It's a big, there's lots of things that get sent there. Okay, so that's a big thing. That's part of our theorem. It lets me draw the first leg of our picture. So we have our group G, and we're sending through this map that we now know exactly how to define phi to G mod H. And it's onto, and it's a homomorphism. Okay, so this is theorem 1, by the way, in this section. I think the next thing to look at is what they call, I'll use his numbering, part 3. G is abelian, then the quotient group is also. How would we prove that? How can I prove that G mod H is abelian? To prove abelian, I pick how many elements? 2, right? So choose AH, BH in G mod H. That's what the elements look like. Then AH star BH, the operation of those two cosets is by definition equal to AB H, right? Well, what do I know about AB in this case? It's equal to BA. Why?
It's commutative.
Because G is commutative. That step is because G is abelian, right? But by definition of coset operations, what's that equal to?
BHA.
Yeah, it's equal to BHAH, right? Therefore, G mod H is abelian. Okay, what else is preserved? Turns out homomorphisms preserve a lot of stuff. As we discussed when we went over them, they preserve the identity. Let's grab that one next. He doesn't elicit it, but that's an important thing to remind ourselves about all homomorphisms. Under this map, what is phi of the identity by definition?
EH.
EH, right? Which is E? Which is H? And H is the identity, right, in the quotient group. So identity gets mapped to the identity. That's an easy one-liner, and that's always true of any homomorphism. Okay, something else that happens. Is if G is cyclic, this is property 4. So is G mod H. What does it mean if G is cyclic? What does G look like? So this means that G is generated by a single element. It's the set of all the powers of A. Which may or may not be finite, but that's what all the elements look like. Some power of A. So if I take an arbitrary element, choose G in G, then phi of G is equal to G H, right? Well, what does G look like? If it's a cyclic group. Yeah. But remember, this math was what? Phi was what? As a function? Onto. Which means I can write every element of, because phi is onto, every element of G mod H looks like K, for some integer K. That's the very definition of a cyclic group. Therefore, G mod H is cyclic with what generator? Well, where does A itself get sent? Where does A itself get sent by my map? The generator. To AH, right? In fact, it's equal to Because if I start with AH, I can get all of these, right? Okay, so cyclicity is preserved by this coset method. And there's more. I'll lose that. What else is there? Property number 5. If the index is finite, what's the index? The number of cosets. So it doesn't mean G is finite, but the number of cosets is finite. Then the size of GH is equal to this index. How do we know? Well, that's almost definitional, isn't it? This is how many cosets there are, and what is this? What is G mod H? It's the collection of cosets, right? That's all it is. It's a symbol for the collection of cosets. So that's basically by definition of the index. It just means the number of cosets. But further, the important part of this, if G is also finite, then from our previous theorem, actually Lagrange's theorem, the size of G mod H is equal to the size of G divided by the size of H. How do we know that? Lagrange's theorem says that the size of G is this times that, right? But in the case of this is that, right? So this is just a direct application of Lagrange's theorem. So this is real handy, but it only works when G is finite because I have to compute this number and divide. Okay, a couple of trivial examples. It should be clear that that's a normal subgroup of any group, because the identity commutes with everybody always. What would be how many cosets? What's the size of that element, of that coset, or of that group? One, right? So how many different cosets must I have? The size of G, right? So the cosets, this is actually a set of all, these are cosets, right? What would be the coset associated with the element G? That would be G star E, right? This guy just absorbs all the things. So this is called the, if it's finite, these are singletons. That is sets with one element in them. And it's clear that this is really just funny way to write G. So G mod E is isomorphic to G. By the trivial map, I send each of these singletons to its element by itself. So when I mod by just the trivial subgroup, nothing happens, and this is the point. And conversely, G is normally G for sure. And that only has one element in it, right? That's just a single coset G. And so this is isomorphic to just the identity because this is the identity in the quotient group or the factor group. Okay, one more little thing. Let's get this back on the board. We've had it before, but now that we've got better background. So now I've got a map between two different groups. G and H are two groups. And let K equal the kernel of phi. That's what is the kernel of a map? Set of all elements of G, right? That gets sent where? The kernel of a map. Set of all elements in the domain that gets sent to linear algebra, they get sent to the zero vector, right? And it's sent to the identity, such that phi of G is E in the target. That's the kernel. I want to prove that's a normal subgroup. How do I prove normality? Let G be some element of G. I need to show that GK is equal to KG. Or equivalently, as our textbook points out, you can do this kind of math. And this is the one we're going to use. So let X be an element of my kernel. Then what happens under that map? Phi of G times, that's the X element, right? Not a multiply sign. Well, it's a homomorphism, so that's phi of G times phi of X times phi of G inverse. But what's phi of X? It's in the kernel. It's the identity, right? And what did we learn about homomorphisms? That's the same as phi of G times phi of G inverse, right? Homomorphisms send inverses to inverses, and that's also the identity. But if G x G inverse gets mapped to the identity, we just showed it, where must it live? show gx g inverse gets mapped to the identity, where must gx g inverse live? In the kernel. Implies gx g inverse is in the kernel. So we just proved that gk g inverse is contained in K. The other way is trivial. Pick an element in K. Is it trivial? Show what's in there. Yeah, because no, it's not trivial. That's not the wrong point. Okay. So, exercise 2.9, really do A. It will take 2 pages of work, but maybe 1 if you're careful. Yeah, I think that's enough for now. So, Friday, we'll discuss we've already done it, but we'll go over 2.10, the isomorphism theorem, and that'll really wrap up our group theory. And then next week, after this week, we have 2 weeks left, which we'll use to lightly discuss where we started, rings and fields. So we'll kind of come full circle. And then all we're going to do the last week of class after we return is practice, 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 practice for the plan. Okay, so thank you, and we'll see everybody Friday.